Let's now talk about the energy in a chemical reaction. As you may know, some reactions will release heat and some will take in heat. For example, if I show you this reaction of aluminum reacting with iron 3 oxide, you might guess that this is a reaction that releases heat, right? So actually this is the reaction that welders use for hundreds of years to create something that is hot enough so that they can melt metals. Right? So in your everyday life you may have experienced this already. Let's say for example in the winter you go up to the mountains where it's very cold and snowing. You want to protect your hands from freezing. What do? You bring a hand warmer, right? When you activate a chemical hand warmer, the molecules in that bags will start to mix and will react. In that reaction, heat will be released into your hand, keeping your hand warm. And so even though heat is a product of these reactions, sometimes heat is also required. And as we know, heat is an energy. So energy is required for all reactions, it turns out. There are three main conditions that are required for a reaction to occur, and they all kind of deal with the amount of energy that is available. The first condition is that when molecules react, in order for them to react, they must meet, they must collide. The second condition is that when they collide, they must collide at the right orientation. If they weren't colliding at the right orientation, they will just bounce away from each other and nothing will happen. And the third condition is that they must have the correct amount of energy. This energy is called the activation energy. If we draw an energy diagram where the y-axis here represents energy and the x-axis represents just the reaction coordinate or the progress of the reaction. In one hand you may have a reactant. Let's say the reactant has a certain amount of energy. And on the other hand you have a product. It also has a certain amount of energy. It turns out for a reaction to occur, for the reactant to become a product, it can't simply transition from this energy to this energy. You have to put in a little bit of energy before falling down into that energy of the product. This amount of energy is called the energy of activation or the activation energy. You can imagine this almost like a hill analogy, right? So if you are standing on this side there's a hill and you're standing on this side and you want to get to this side. In order for you to get to this side, first of all, you have to climb that hill. So you have to require some energy until the very top. Once you're at the very top of the hill, you don't need any more energy. And if you continue to walk that way, now you're actually releasing energy, right? You don't even have to put in energy to fall back down. Same kind of idea with reaction. Let's take a look at two different types of reactions. Like I said before, if you're releasing energy, that's one type of reaction, and if you're absorbing energy, that's another type of reaction. Let's talk about an exothermic reaction first. In an exothermic reaction, heat is released, right? The word exo is outside, heat is going outward. So in an exothermic reaction, we see that the energy of the product is lower than the energy of the reactant. Because the energy of the product is lower than that reactant, when reactant converts into product, you are releasing that heat, right? You have to subtract that energy from the high energy of the reactant. To annotate that heat is being released, we often write heat on the product side. For example, there, in that chemical reaction, you see that plus 18 kilocal. That's the amount of heat that is released and is written on the product side. Again, to note that the reaction is exothermic, the energy of the reactant is higher than the energy of the product. On the opposite case, when we have an endothermic reaction, instead of the energy of the reactant being higher than the energy of the product, it's the opposite. So if this is the reactant and this is the product, for you to convert from the reactant to become a product, again, you have to give energy to it, and once you give enough energy, it falls back down to become a product. And again, this energy is called the activation energy. Alright, so when you see an energy diagram with the reactant being lower in energy than the product, you know that is an endothermic reaction. Again, the word endo means inside, going inward, so the energy is going into the system. you see that heat is added into this reaction for it to occur, so heat is a reactant. So heat is written on the left-hand side of the chemical equation. Now let's talk about the rate of a reaction. Some reactions take very long time, and some reactions happen very quickly. So what determines the rate of a reaction? The first is temperature. How do you think the temperature will change the rate of a reaction? Imagine you have to cook, right? What do you do when you cook? You add heat to it. And cooking is very much a chemical reaction, right? Once you add small amount of heat to that, it might take longer time to cook. Whereas if you add high heat to that, a lot of heat to your cooking, it will cook faster. And so why is it that temperature affects the rate of reaction? Remember we talked about the 3 conditions for a reaction to occur? So when you have high temperatures, the molecules are actually moving faster. And when molecules are moving faster, there is more energy. And so that when these molecules collide, they have enough energy to overcome the activation energy, and therefore the reaction will proceed. And if more of your molecules are moving fast like that, then more of your molecules will react. Therefore, the rate of the reaction will increase. Another factor to increase the reaction rate is increasing the concentration of your reactant. Right? So how does increasing the concentration help? Going back to, again, the idea of how a reaction occurs. For a reaction to occur, it must collide. So if you increase the amount of reactants you have, their chances of colliding will also increase. And the last way you can increase the rate of reaction is by using a catalyst. And the job of the catalyst is basically to lower the activation energy, providing a different pathway. Instead of going on this hill, it provides a different hill. Right? So if there's a different hill to go by, and that hill is lower in energy, then you require less energy to have a reaction. You may not know it, but you actually do know of many catalysts. Basically, everything in your body, all the enzymes in your body happen because of catalysts. These are called enzymes. They are biological catalysts. Without these catalysts, the reactions in your body, the biochemistry will be very, very slow, and you will not be alive.